Yesterday you guys started on this lab on Hooke's law. Hooke did some stuff with springs and force and what's called elastic potential energy. Okay, we've talked about kinetic energy, which is energy due to motion, and gravitational potential energy, which is the energy an object has due to its height and gravity pulling on it. Today and yesterday you were looking at work done stretching a spring, and then work is actually the transfer of energy. So when you do work to stretch a spring, the energy is stored in that spring. So it's stored as elastic potential energy. Okay, so you guys went through and did all this, and it says, okay, do the points appear to be in a straight line or in a curve? And I have some data here that I collected. Okay, and so you can see 0, 0, and then my force goes up. And that looks fairly linear, and I'm hoping that's what you guys saw. It says fit the appropriate curve to the graph and record that equation below. You can either do this on your iPad through graphical analysis, or you can do it right on the LabQuest. If you do it on the LabQuest, then you just highlight those points and you do analyze. Gonna let me do that now. Analyze, and your curve fit. And since they do look like a linear graph, I'm going to choose a line from here. Now it tells me the equation of this line, y equals mx plus b, but it doesn't tell me necessarily the units. It says on number 2 to record the equation of that line and include units. So what are the units with that? Well, let's take a look. Okay, we've got y, which is the left side of my graph, which is force, so that's newtons. B, which is almost exactly 0. And think about it, if you're not pulling on the force on the spring, then as it stretched out, it should be exactly 0. And this is close enough that I'm going to call it 0. So y equals mx plus b, where y is force, x is length, and m is 9.98. And we got to think about that. Okay, so if we come over here and we've got y equals mx plus b, what I really have is force equals mass times x, which was length, sorry, the m is not mass, m is slope. Force equals slope times length plus 0. And so what I have is force equals 0.9 or 9.98. Now I got to go back and look. 9.98 plus 0. And so this is times x, which is length. Okay, so and x is usually x. Okay, so what are the units of that slope? Well, force is measured in newtons, right? The slope has got to have units so that when we multiply it by meters, it is in newtons. So this must be newtons per meter. Okay, so I have force equals 9.98 newtons per meter times x in meters. It says use the graph to predict how much force would be necessary to stretch this spring to 18 centimeters. Well, you put that in there, and 18 centimeters, this is not meters, so I'd have to take 9.98 times 0.18, and then I could get how much force would be. Then actually stretch the spring that far and see what you get. These springs and the force sensors are good enough that you should be within 0.2 newtons. So you should be able to do that pretty close. Repeat the process for the other springs, recording the equations for each spring. Okay, how does the slope change as the springs get stiffer? Generally speaking, what I'm hoping is the slopes get steeper, slopes increase, and the reason for that is more force is required to stretch it. So that slope of that line, this part talks about, is called the spring constant. The general form of the force exerted by a spring is called Hooke's law and has the form F equals negative kx, where k is the spring constant and x is the distance it's stretched. Why does the equation contain a negative sign? Well, let's think about it. Okay, when you have a spring, okay, and it's fixed over here, you pull this way, so your force is that way. The spring pulls back to the left this way, so the force the spring exerts is actually opposite the force you exerted, so it's negative kx. So the force done to stretch a spring is negative kx. Now, this is where we get into, okay, so what's up with Hooke's law? Okay, so you had this graph, and down here you have meters, and over here you have force, and your line goes like that. It says, what is the formula for calculating the work done by a force moving through a distance? Well, work is equal to force times distance times the cosine of the angle between them. But since you were moving the force probe in the same direction as the motion, that angle is 0. So I'm going to leave it off for now. What property of the graph shows the work done to stretch the spring a distance x? Well, over here I have force, over here I have distance, so this is the area underneath. The area under that curve shows me the work done. So area. And how do you calculate the energy stored in the spring then? Well, think about this. If the area of that is what I want, then the area of that triangle is 1/2 the base, which is x, times the height, which is f, right? And that gives me the area. But the force is really kx. Okay, so the energy stored in a spring is given by 1/2 kx squared, where k is the spring constant and x is the distance the spring is stretched. Okay, that's elastic potential energy. The elastic potential energy stored in a spring is 1/2 kx squared, and that comes from work equals force times distance, and work done is the change in energy of an object. Okay, so we're going to use that relationship today a little bit with some problems, but hopefully you can finish up the lab and you do see some fairly linear things.